medium is equal to sine of angle of refraction divided by sine of angle of incidence. Let's now talk about total internal reflection. Total internal reflection occurs only when light travels from a denser medium into a less denser medium. For example, when light travels from water into air, or when light travels from glass into air, this can happen. Now look at different rays of light traveling from glass into or water into air. You can see as light travels from water into air, it will bend away from the normal. The angle of refraction is greater than the angle of incidence. Now you can imagine for a particular angle of incidence. Now, since the angle of refraction is greater than the angle of incidence, for a particular angle of incidence, the angle of refraction will be 90 degrees. Now, if now the angle of incidence, if now the angle of refraction is greater than 90 degrees, where will the reflected ray go, or the refracted ray go? It cannot go into the less denser medium, means it will be sent back to the denser medium. So the particular angle of incidence for which the angle of refraction is 90 degrees is called the critical angle. The critical angle. You see, for a particular angle of incidence, the emerging ray will go along the surface. That means the angle of refraction will be 90 degrees, and that particular angle of incidence is called the critical angle. If the angle of incidence now is greater than the critical angle, the light ray will not emerge, it will be reflected back into the denser medium. Well, and that is a very important and very interesting phenomenon. Now this diagram shows light traveling from water into air. You can see a lot of light is passed from water into air, and a part of it is reflected. As the angle of incidence is increased, you can see the angle of refraction is nearing 90 degrees there. That means you can see that is the angle of, now this particular angle of incidence is called the critical angle, and if you increase the angle of incidence beyond that, all the light is reflected back. No light escape into the less denser medium. This phenomenon is what we call total internal reflection. Now here I have the illustration. This is the critical angle. The incident ray, the refracted ray, the angle of refraction is 90 degrees. So the angle of incidence in the denser medium for which the angle of refraction is 90 degrees is called the critical angle. When the angle of incidence in the denser medium is equal to the critical angle, then Snell's law can be written as, you know that N1 divided by N2 is sine of angle of refraction divided by sine of angle of incidence. When angle of refraction is 90 degrees, the angle of incidence is called the critical angle theta c. And therefore sine theta c equal to N2 over N1, because sine 90 is 1. Now here I have another illustration. I don't know whether it comes out well in the movie. Well, here this is a laser that goes from water to air, and here the critical angle is greater than the angle of incidence is greater than the critical angle, and you can see how it is totally reflected. That's a beautiful picture. An example. What is the critical angle for light traveling from glass into water if the refractive index of glass is 1.5 and that of water is 1.3? Here we have a situation, light traveling from glass into water. Glass is the denser medium, water is the less denser medium. And simply we can use sine theta c equal to N2 over N1. N1 is the refractive index of the first medium, N2 is the refractive index of the second medium, here it is water. So we got refractive index of water divided by refractive index of glass will be sine of theta c, and that will give you theta c, the critical angle is 62 degrees. Let's now look at dispersion of light. Dispersion of light. You see, you know that light consists of over 3,000 different wavelengths. Now, when each of these wavelengths undergoes the deviation, the angle of deviation or the angle of refraction will be slightly different for each wave. Now, that can create the different wavelength dispersing or spreading apart. Well, the extent to which a light wave is bent by a material medium such as glass depends on the wavelength of the light wave. Now, that means if white light is allowed to pass through a prism, each wavelength will be bent slightly different from the other. A shorter wavelength corresponds to a greater frequency, a greater energy, and a photon of greater energy gets deflected more than one of lesser energy. You see, it's like that. If you travel very fast on a bicycle, and if your speed changes suddenly, you tend to deviate much more than if you were going slowly. That is why slow speed is safer. In the same way, a very energetic photon gets deviated more than a less energetic photon. For example, a violet photon carries more energy than a red photon. So if you pass white light through a glass prism, what comes out is actually a dispersed form of all these wavelengths. So as a result, when a ray of white light enters a glass from air, violet color will bend more than red. The effect is more pronounced when a narrow beam of light is allowed to pass through a triangular glass prism. Now, that's a beautiful phenomenon. The emerging light will spread into its constituent colors as we... Now, in the last lesson, I showed you that although we say this is red, that's a combination of several hundred wavelengths. Now, this phenomenon is what we call dispersion of light. Now, dispersion occurs because refractive index is different for different colors. Now, we talk about refractive index of a material. Actually, refractive index of glass has different values for different colors. Glass has a refractive index for red. It has a different refractive index for blue, a different refractive index for violet, because each of these colors will be bent in slightly different angles. Alright, the refractive index for ordinary glass for blue light is 1.53, and for red light it is 1.51, slightly, distinctly different. Well, now let's look at lenses. When light is incident on one face of a prism, it undergoes refraction twice while emerging from the other side. Now, how does that happen? The result is that the emerging light bends towards the base of the prism. Now, I think I can show that to you. Let me see if I have that demonstration. Now, here I have a triangular prism. This is the base of the prism. I have allowed 3 light rays to go into the prism. They bend while entering the prism and bend again while coming out. You can see the 3 light rays coming, they all bend towards the base. You can also see the concept of dispersion here. All of them have actually spread into colors. Look at the beautiful colors there. So a light ray, while entering a prism, undergoes refraction twice and bends towards the base. So when a ray of light passes through a prism, the emerging light bends towards the base of the prism. By combining prisms suitably, so if I put two prisms, the base of each prism facing each other, and I allow light to go through the combination, light will bend towards the base of each. It means that will act as a converging system. So this is the principle of working of a lens. If you watch here, now these are actually lenses put so that the bases are facing, and if you allow a beam of light to fall on it, they will all converge to one point. And on the other hand, if you put the prisms the other way around, if the bases are facing in the opposite direction like these, then it will produce divergence. So by suitably combining prisms, you can produce converging lens or a diverging lens. Alright. Place two prisms, the bases are facing each other. What do? They produce convergence. And if I reverse the prisms so that their bases are opposing, they produce divergence. Well, this is the basis on which lenses are constructed. Now here I have a lens which is actually the prisms, the bases facing, and you can see what it does. It actually produces convergence. If you notice, the light rays are all converged. Whereas if I use a concave, a diverging lens, it produces divergence. So this is a diverging lens, and this is a converging lens. Now I want you to watch that convergence. The point where they meet is actually beyond the screen. Okay, let's go back to the... So we have two types of lenses. One is a converging lens and the other is a diverging lens. Alright. One half of a convex lens, if you look at this convex lens, which is a converging lens, if you take one half of it, it can be considered to be part of a sphere. And the center of such a sphere is called the center of curvature of the lens. We traditionally mark it as 2f. 2f is the center of curvature. Now there are two centers of curvature. There is a center of curvature on the right side and a center of curvature on the left side. The geometric center of the lens is called the optic center. That's the optic center of the lens. The distance from the optic center to the center of curvature is called the radius of curvature of the lens. A line passing through the center of curvature and the optic center is the principal axis of the lens. All these are similar to the terms we defined in the mirror. Now, rays of light that are parallel to the principal axis, a ray that is parallel to the principal axis after refraction will pass through a point on the principal axis, and we call that the principal focus. So this is a ray that is parallel to the principal axis. After refraction, it will pass through a point on the other side of the lens, on the principal axis, and that point is called the principal focus. The distance measured from the optic center to the principal focus is called the focal length of the lens. The lowercase f, the same we used for the mirror. So the focal length is the distance from the optic